Hello and welcome. This is going to be our lecture video for April 22nd. Going to be talking about the Pythagorean identity today and just doing a lot more practice with what we were talking about last lecture. All right, so let's go over domain of validity again. So what you want to do is go through your identity, the very first identity as it's originally written, and above every trig operation, you want to write what ratio in a right triangle that it represents. So everywhere I see a sine, I'm going to write O over H for opposite over hypotenuse. Everywhere I see a cosine, I'm going to write A over H. Everywhere I see a tangent, I'm going to write an O over A, and so on. And then you're going to go through and only circle what's in the denominator. All right, so if one of these trig functions is in the denominator of a bigger fraction, then you circle both of these. But if it's just like a sine by itself, you just circle the h. If it's just a secant by itself, you just circle the a. Now, hypotenuse can never be equal to 0, so this will never lead to issues of undefined trig functions. But opposite and adjacent can be equal to 0, and it happens at multiples of 90 degrees, or pi over 2. And if you have just opposites, then this expression here represents when that's going to be equal to 0, and you'll have undefined. If it's just adjacent, you write this. If it's both, you write this. And this can just be memorized. This is a little bit more simplified than what we were writing the other day, just n plus 1/2 pi. So you've got n pi, n plus 1/2 pi, and n pi over 2. All right. So what is the domain of validity of this identity? So we're not verifying this identity yet. We'll practice more of that later. All we're asking is what's the domain of validity. So I want to go to each trig function and write its ratio. So when I see secant, I'm going to write hypotenuse over adjacent. When I see cosecant, I'm going to write hypotenuse over opposite. And when I see tangent, that's opposite over adjacent. Now I circled just what's in the denominator. I've got an a in the denominator, an O in the denominator, and another A. We go back to the table, we have both, so we're going to use this one here. X cannot equal n pi over 2. So x cannot equal n pi over 2. Okay. So, do we know what an identity is? An identity, an equation that's true for all possible inputs. And the thing I said the other day is that it's so true that it doesn't need to be proven by itself. These are the quintessential trigonometric identities. There's more, and we use these ones that don't need to be proven to prove these more unusual ones that are kind of just lots of different random trig functions thrown together. These are like nice and simple and elegant, and then we use them to verify much more complicated equations. So we use these to verify these. All right. Goal for today is to understand the origin of the Pythagorean identity and to start simplifying and verifying trig expressions. Why are we doing this? When we combine trig with our units on algebra, it gives us a lot of opportunities to practice both. So, I think I said this last lecture, this is a very algebra-based look at trigonometry, and that's what kind of differentiates it from our last unit, which more of a geometric look at trigonometry. So, how to show your work in a trig verification problem. Now, the key here is that when we're doing trig verification, it's all about the work. There is no numerical final answer. It's the work is the proof to show that the relationship is a valid relationship. So whenever we use a reciprocal identity, you're going to draw an arrow wherever you use it, identity, and then you're going to put an R on that arrow. All right, if you ever use a quotient identity, you're going to draw an arrow and you're going to put a Q on it. the quotient identity is just the tangent and cotangent identity. So if you want to do a t, that's what I did last class, but I looked back at my notes, I use q much more often for quotient identities. And here we can go back to this. So there's your reciprocal identities, there's your quotient identities, and the one we're going to learn about today is the Pythagorean identities. And if you ever use one of these, often these are the trick to like a really tough trig verification. You're going to write P on your arrow. So I'll just say write a letter on your arrow. All right. Here, a little bit more practice from the homework. Here's number 17 in the homework. We're going to verify and state the domain of validity. So cotangent of theta times secant of theta equals cosecant of theta. Don't let it throw you off that we're using theta instead of x. It's really, there's no change there. It just means that when we show our work, we want to be using theta. All right, so I'm going to use a quotient identity on cotangent to rewrite it as cosine over sine. And I drop the theta anyway while showing my work. The secant, I'm going to use a reciprocal identity to rewrite that as 1 over, that's a multiplication symbol, 1 over cosine. And then I'm going to use a reciprocal identity on this, the cosecant, to rewrite it as 1 over sine. All right, so that's how I'm showing my work. I'm drawing those arrows. Also, a good point of style on these trig verifications is you try to not use any balanced operations. You don't try to ever cross the equal sign. You only simplify one side at a time to try to make it match the other side. And there's the reason you do that is there's kind of some ways to cheat. If you move things from one side to the other, you can like kind of secretly divide by 0 when you're not supposed to. So it's better to just simplify one side at a time. And that's a better way to verify things. All right, so I got fraction times a fraction. I can cross simplify by crossing out these cosines. And now I've got 1 over sine. Now it's a good time to bring back that theta. 1 over sine theta equals 1 over sine theta. This is true just by the definition of equality. So we're going to draw our little box to show that we have verified it. Then we're going to go back up to the original problem and write the ratios. So cotangent is adjacent over opposite. Secant, hypotenuse over adjacent. At this point I see I've got both already, but I'm going to keep going. Cosecant is hypotenuse over opposite. I've got both opposites and adjacents in the denominator, so I say theta cannot equal n pi over 2. Let me go back and check that that's right. N pi over 2, yep. All right, the Pythagorean identity. Here's where it comes from. So let's imagine drawing a triangle into our unit circle. So this is our unit circle. And we're going to draw just a generic triangle on in here. And I'm going to keep everything color-coded. So in this triangle, the red line is 1 unit long because this is our unit circle. So the radius has to be 1. All right, if that side length is 1, then this side length over here for some angle theta must be sine of that angle theta equals this side length. We'll call it, I don't know, A for now, divided by the hypotenuse, which is 1. So anything divided by 1 is just itself. So this side length in here is just sine of theta. So I can just erase this side here. That length there, once I know theta, I take sine of that theta and I get that length. All right. Similarly, if I take cosine of that angle theta, cosine of theta is going to equal adjacent, this side length here, we'll call it b for right now, divided by hypotenuse, which is 1. B divided by 1 is just b, so this length in here is just cosine of theta. So for any triangle in here, the opposite, if the hypotenuse is 1, the opposite is sine of theta, the adjacent is cosine of theta. Well, now let's set up the Pythagorean theorem. A squared plus b squared equals c squared. So, I did this a little bit backwards because I wanted sine to come in and be blue. Let me fix my coloring. I want that to be a squared plus green b squared. All right, let's fill in sine for a. So I've got sine squared. Also, when it's sine of theta squared, one thing you do is you put the squared right after the sine, so it's sine squared theta. The reason you do that is if you put the squared at the end, it can sometimes look like you're just squaring the angle, but you're not just squaring the angle, you're squaring the entire trig operation here. So you put the squared right there. All right, so plus cosine squared theta equals 1 squared, and 1 squared is just 1. And that is your Pythagorean identity. Sine squared plus cosine squared equals 1 is how we say it. Very good one to memorize. All right, so that's where it came from. Let's start using it to verify some identities. So 1 plus tangent squared x equals secant squared x. All right, so what can I do? One, I can use the quotient identity here. I'm just take a quick pause. Okay, so I'm using the quotient identity to replace tangent here. Well, it's tangent squared, so this is actually going to become sine squared over cosine squared. Hopefully we're all okay with that. This will still just be a 1 over here. And then I'll go ahead and use a reciprocal identity to swap out secant squared for 1 over cosine squared. So the squared has to come along when you use that reciprocal identity. Okay, so I've got 2 things equals 1 thing. So the idea is to take the more complicated side and make it look like the simpler side. So I've got to find a way to combine these. So I need a common denominator. So I'm going to replace this 1 with a cosine squared over cosine squared. Now I've got a common denominator. That's a squared s equals 1 over cosine squared. Now I'm going to combine these. But I'm going to bring the sine squared in front so it looks more like the Pythagorean identity on top here. So I've got sine squared plus cosine squared over cosine squared equals 1 over cosine squared. All right, and then as I rewrite this, I'm going to write it over here and use a Pythagorean identity for the first time. So I'm going to write a p. Sine squared plus cosine squared is going to become a 1. So I've got 1 over cosine squared equals 1 over cosine squared. Now the 2 sides match. I guess we could do domain of validity. It doesn't say do domain of validity, so we'll skip it just in the interest of time, but for most problems you want to write that. This one very similar. Try to use I recommend you pause the video here, try to use a similar technique to verify this one on your own. Give you just 1 second to do that. Okay, here's this one. Written down, its domain of validity, I did write it for this one, is x does not equal n pi. I guess we'll go back and do this one. All right, tangent, opposite over adjacent, secant, hypotenuse over adjacent. We have only adjacents. So what does our table tell us? N plus 1/2. So x cannot equal n plus 1/2 pi. At some point we got to write n as an element of the integers. All right, there's the one that you just practiced. So here's the one that we figured out using the unit circle. Here are the two that we just verified. Together, these three are like our quintessential Pythagorean identities. The only one you need is that first one. You can always use that first one to get the other two like we just saw. All right, so here's sort of my broad notes on how to simplify anything with trig. The first step, it's called decompose into sine and cosine. You can use the reciprocal identities and the Pythagorean or the quotient identities to turn anything into sine and cosine. And when you're only dealing with the sine and cosine, it makes things a little bit easier. Then you want to cancel everything that's possible. Then normally, if it's still looking tricky, the key is you've got to use one of those Pythagorean identities, especially if you see squareds anywhere, because they all have a squared. And then recombine using the quotient identities if possible. All right. On the calendar, there's a worksheet titled Math Humor that has got some good extra practice problems. Take a look at that. Okay, let's do one last one. I think this is our last one. All right. And this one is pretty tricky. So definitely need some space for this one here. All right, so the idea is turn everything into sine and cosine. So I'm going to use a quotient identity on tangent squared to turn it into sine squared over cosine squared. I'll leave the sine squared alone right now, and I'll do the same on this tangent squared. Turn it into a sine squared over cosine squared times sine squared. All right, when I multiply something to a fraction, it goes to the top of that fraction. Over here, I want to combine this into one fraction, so I need a common denominator. So I'm going to multiply this by cosine squared over cosine squared. So I'm only working on each side. Here, I'm going to make them meet in the middle. I'm not going to try to turn one side into the other side because they're both pretty complicated. But I'm not going to cross the equal sign. I'm only going to do operations that I'm allowed to do to one side, like multiplying by forms of one. Okay, let's see what we got now. Sine squared over cosine squared minus sine squared cosine squared over cosine squared equals sine squared times sine squared is going to become a sine to the fourth over cosine squared. All right, on this side over here, this is going to become one fraction. So it's going to be sine squared minus sine squared cosine squared all over cosine squared equals sine to the fourth over cosine squared. Here, both of these terms have a sine squared, so that can be factored out. So this is going to become a sine squared times 1 minus cosine squared all over cosine squared equals sine to the fourth over cosine squared. Now, whenever you have like a 1 minus cosine squared or a 1 minus sine squared, off to the side, you can take the Pythagorean identity, which is sine squared plus cosine squared equals 1, and rearrange it to match this. So I'm going to subtract cosine squared from both sides. And now I get sine squared equals 1 minus cosine squared. And then I'm going to use this to substitute in here. So the much easier way to do it is to do the scratch work off to the side. And so this here can become a sine squared. And that right there, we use the Pythagorean identity. We used the scratch work over here to rearrange it, but we're still using the Pythagorean identity. So sine squared times sine squared over cosine squared equals sine to the fourth over cosine squared. And we get sine to the fourth over cosine squared equals sine to the fourth over cosine squared. Those two balance. Let's go back up to this. Opposite over adjacent, opposite over hypotenuse, opposite over adjacent, opposite over hypotenuse. We have only adjacents in the denominator. So this is valid as long as, and we used x as our variable, x does not equal n plus 1/2 pi. Which I think it's the same as this one. N plus 1/2 pi, yeah. Okay, call it good there. Have a good rest of your day.